So I have shown that transmission by inhalation of aerosols can happen at both short and long range. And now we'll talk about why size is so important. Next. The figure on the left is shown just for scale. A human hair is about 50 to 70 micrometers in diameter. We talk about PM 2.5 and PM 10 air pollution particles. Those are 2.5 and 10 microns. The virus that we're talking about is 0.12 microns in size, so much smaller even than our PM 2.5. It's similar in size to influenza virus. And then I've shown a couple of other respiratory viruses. Those are a little different because they're non-enveloped. Next slide. The size of that droplet or aerosol that's carrying the virus is critical. I'm going to spend some time here because this is one of the most important things for understanding transmission by aerosols. First of all, the airborne virus is not expected to be naked in the environment. It comes out in respiratory fluid, which contains liquid, water, and other solutes from the respiratory fluid. I'll show that in another slide. So even though the virus itself is around 0.1 microns in size, those droplets, aerosols and droplets in which it comes out from is released by a person, range in size from anywhere from 0.2 microns, smaller than that, to 100 microns or larger. Next. It is the size of this carrier droplet or aerosol that defines the transport of the virus in the environment. The size of the virus itself is irrelevant. Next. These different transport properties include how long the virus can stay aloft, how far it can travel, how quickly it falls to surfaces, where it deposits in the respiratory system, how efficiently it is removed by masks and filters, and the physics is going to be the same for all viruses that are in, as long as they're in a droplet that's the same size or aerosol, it's going to behave the same way in terms of physical transport. Next. Now, the differences between different viruses come into play with some other factors that have to do with the biology of the host, the pathogen, or the susceptible individual. So first of all, the viral load can differ between different viruses. Some viruses may end up having a much higher load in respiratory droplets. It's possible that the distribution in different size droplets and aerosols could differ. There could be, for example, maybe more of measles virus in the smaller ones. The inactivation rate of different viruses in aerosols matters also. We know that this varies depending on the virus. Even different strains of influenza virus have different decay rates in droplets and aerosols. And then it also depends on the location and the dose in the respiratory system of where this needs to initiate infection. So tuberculosis, for example, can only initiate infection deeper in the lungs. So there we're talking about aerosols that are smaller than 5 microns. One other factor is pre-existing immunity that's going to affect what we observe about the spread, the transmission of viruses in droplets and aerosols. Next. So as I mentioned, size is critical for determining how long these droplets or aerosols can remain in the atmosphere. We can calculate this based on the particles on the droplet size. Based on Stokes' law, this graph shows the time for a droplet or aerosol to settle from a height of 1.5 meters, which is the height of a typical person's nose or mouth, as a function of the diameter of that droplet or aerosol. So you can see that for things larger than 20 microns or so, those are only going to stay in the air for minutes or just seconds. But once we get down to smaller sizes, next, smaller than 10 microns, those can stay suspended for many minutes. As we go to smaller sizes, we're looking at minutes to hours. Next. Here's where 5 microns falls on this graph. It has a settling time of over 30 minutes. Next. During this time, the droplets can travel. So we're looking now, of course, there's 2 different travel distances we should be thinking about. One is just in that respiratory plume that is emitted by a person, but that relaxes within a few seconds, and then any aerosols that are still floating in air are subject to transport by air currents, local air currents. And so here I'm looking at the trajectory of droplets released from a height of 1.5 meters. And in a couple of different scenarios, one is with a low indoor air velocity of about 5 centimeters per second. Even if the air in a room is still, it's moving around. And this would be an extreme case if that velocity were directed in a single direction. But you can see that a 5-micron droplet starting at a height of 1.5 meters can travel over 100 meters, even under low indoor air velocity conditions. We have to get up to a size of 30 microns before we see something that's not going to travel more than 2 meters. Next. Under higher indoor air velocities, of course, these distances stretch out by a factor of 4. And a 30-micron droplet in this case can travel 7 to 8 meters. Next. So the droplets are not just water and virus. Non-volatile solutes in our respiratory fluid compose 1 to 9% of the initial mass of the droplet, meaning that 91 to 99% of it is water. But of the non-water components, we can see that sodium chloride accounts for anywhere from 10 to 72% of it. Proteins account for 24 to 89%. Surfactants, anywhere from 1 to 4%. And even if I have a high viral load in my respiratory fluid, the virus itself accounts for a minuscule percentage of the total mass of that aerosol or droplet, even after we remove the water. The transmission electron microscope image on the right-hand side shows some real respiratory droplets captured on a substrate. And you can see there's kind of a ring around the edge, which is presumed to be the initial droplet size. And then we see what's left, these crystals, after it's evaporated. And by energy dispersive X-ray spectroscopy, those are shown to contain potassium, calcium, chloride, carbon, sulfur, things that we would expect to see in our respiratory fluid. Next. Humidity is important because when we release these respiratory droplets, they're leaving an environment that is fully saturated, near 100% humidity. They hit the ambient air, which is usually not nearly as humid, and some of the water is going to evaporate from those droplets. And we can determine what the final droplet size will be at equilibrium using the Kohler equation, which I won't go into in detail. Next. But if we start with a droplet that is 10 microns in size, it contains salts, proteins, and maybe our virus. They're magnified here considerably. And let's say that we go to a relative humidity of 20% in our room, which is typical for wintertime conditions indoors when it's heated. Next. That droplet will evaporate. Next. And we're going to end up with a final droplet size of about 4 microns. In this case, all the water has evaporated, and now we're left with just the non-volatile solutes, the salts, the proteins, surfactant, and any virus that might be present. Next. Even at a relative humidity of 80%, which is pretty high for indoors, you can see that most of the evaporation has occurred, and we're down near a final diameter that's 0.4 of the initial diameter. I should also note that this calculation assumes a fairly high protein content of the respiratory fluid. We have reviewed information about the composition of respiratory fluid, and a lower number might be around 0.2. So droplets could evaporate to about 0.2, 20% of their initial size. But I think it's going to be somewhere in between 20 and 40%. Next. So I have shown that droplets larger than 5 microns can travel more than 2 meters, and that humidity affects the size and chemistry of these droplets. That chemistry can affect virus viability, but that's a different story. So how did they get into the air in the first place? Next. Well, not surprisingly, coughing produces aerosols. This is work by William Linsey. And he looked at the size distribution of droplets and aerosols produced by coughing. And you can see that he looked while people were infected with influenza and after they had recovered. So over this size range that they measured, from 0.35 to 10 microns, they saw 75,000 total aerosols when the people were sick, and a not significantly different number after recovery. there was note that the variability here, the standard deviation, is rather large, so indicating that there's a large variability in the number of aerosols that people produce. In a follow-up study, they looked at 17 subjects and collected these droplets and aerosols, and they found that viable influenza A virus was found in samples from 7 of those patients in droplets and aerosols ranging in size from 0.3 to 8 microns. Next. Lydia Marasso's group has done a lot of work characterizing the size distribution of aerosols and droplets produced by breathing, talking, and coughing. Here I'm showing some size distributions from speaking and coughing. Note that the scales of both axes are log scale. So their data was used to produce a fit, which is shown by the black dashed line, the BLO model, showing that the distribution is bimodal. It's actually trimodal, but we'll focus on kind of the smaller mode, which is centered around 2 microns, and then there's a larger mode greater than 100 microns. And if we look at the actual number of these droplets and aerosols that are produced, 99% of the number are smaller than 20 microns or so, and only 1% are these larger droplets. With coughing, we see some more of the larger droplets relative to the aerosols. If you want to talk about breathing only, then you would focus just on the smaller mode here, and we remove the larger mode, which is thought to have formed more in the oral cavity. Next. So if I take these numbers, I can calculate the volume of respiratory fluid droplets and aerosols that are produced, which is 5 nanoliters from saying hello world if you're speaking, or 125 nanoliters from one cough. And then if I apply a viral load measured in an early study on COVID-19, I use 7 × 10⁶ RNA copies per milliliter, then saying hello world could potentially release 30 viral RNA copies into the air, whereas coughing could release 900. But that's just from saying hello world, one breath. If a person is talking continuously, sentences, they go on, obviously they can produce a lot more over time. Next. So we have seen that breathing, talking, and coughing release droplets and aerosols that range from submicron to millimeter in size. They may contain virus. We'll hear more about that later. What happens to them once they're in the air? Next.